This program is brought to you by Stanford University. Please visit us at stanford.edu.
This presentation is delivered by the Stanford Center for Professional Development, providing graduate-level education to working professionals, online, on campus, and on-site. For more information, please visit study.stanford.edu.
As many of you know, programming is hard and parallel programming is even harder. Unfortunately, parallel processing is becoming increasingly important because we're demanding things that once were considered high-performance computing and expensive. To address these issues, Intel has been shipping for some time multi-core processors and doing a lot of work to put out more support for parallel hardware. They're also shipping tools to make this hardware more useful. Renee James is VP and General Manager of Intel's Software and Solutions Group, and Wei Li, Senior Principal Engineer, are here today to tell us about some of those tools.
Good afternoon. I want to make a couple of comments about today. We have two presenters because I'm going to give you an overview of what's motivating Intel and the problems that we think we see in the environment, especially the software environment. And then Wei Li, who some of you may know, has taught at Stanford before, PhD in computer science, specifically in compilers and parallel programming. And he's currently the associate editor for the Transactional Programming Languages and Systems. I think you call it TOPLAS, right? And Wei is doing a lot of our forward-looking work, breakthrough work, and of course is a major contributor to what we do in compilers and our thinking there. So Wei's going to go probably as deep as anyone in this room would want to go, and we'll take questions. In the first part, I'm going to give you an overview of what Intel does in this area, what's motivating our activity here, and then Wei will continue from there. Okay? So first of all, many people don't actually know that we do a lot of software at Intel. In fact, Steve McGady, who's joined us in his tuxedo because he and I are going to benefit for Gordon Moore, was actually one of my first managers at Intel in the software group, in the labs, and we were working on 960 tools to begin with and then moved on to more exciting technologies. But in fact, we have been doing software technology to enable our silicon for the greater part of, I don't know, what, 25 years, 20 years at least. Yeah. And what has evolved out of that is actually a robust set of tools and enabling activities to help developers, whether they be in academia and or in independent companies or large corporations, help them to use the performance and features in the underlying silicon. And as it relates to multi-core or parallel programming, we're going to talk very specifically about our activities there. We're a very global organization. We're actually quite a large group of people with highly specialized skills. So we have people who do BIOS work, people who do OS work, people who do compilers, etc. We're all over the world with large teams in Russia, China, Argentina, and then of course in North America. But what it allows us to do is to really try and collect some of the great thinking through our university programs and our efforts to bring in interns. So we've grown sites where we have, very interesting pockets of knowledge and kind of grown up that way and through acquisitions. One of the most interesting teams in the high performance tools is actually in Champaign, Illinois, which doesn't surprise many of you here probably. A lot of graduates from. One unique piece about the organization that I run is that we are completely cross-platform. And I mean that from a software perspective. We do work on Linux. We do a tremendous amount of work. Obviously, it goes without saying in Windows, but we also now do the Apple work as well as Solaris. I think if you probably haven't missed the announcement that most of the major system suppliers are using Intel Silicon. We're deeply engaged in open source Java as well as Java with Sun, VMware, Zen, and other contributions. I was just telling Steve that our team has really embraced open source, and we're doing a tremendous amount of work and contributions. We've been very focused on virtualization and the OS and the BIOS layer, but we're kind of moving on now. And one of the things that we did most recently is we open sourced one of our threading libraries called the Threading Building Blocks and put it out because we decided that it was actually more beneficial to the market for us to move things forward by putting out a library than keeping it for ourselves. And revenue wasn't our objective. Our objective is actually to help people to be able to use multi-core and to do parallel programming. So we have a variety of products. Wei's going to talk about a few of them. I'm just going to give you a very brief overview. Obviously, people know us for our compilers. People in the industry, certainly who want to get high performance, know us most for our compilers. We have an exquisite team, which Wei is part of. We have analytic tools, performance libraries, as I said, and we're going to talk more about the threading tools specifically. We're not going to talk about our cluster tools today, but it is another thing that you can get access to online. We have a lot of this technology now in forums online where you can get sample code, you can blog about it, you can join virtual training sessions about it through Second Life or other. We have a bunch of new things that we've launched in the last year to help people get engaged with Intel on all of these topics. Okay, so specifically, in the last 18 months, we have become very focused on putting together a set of tools for parallel programming. And starting with what we know and love, we've added the Threading Building Block product, which I just told you we open sourced a version of it. We've added the threading analysis tools, and we have a couple of new tools that will be coming out in the next year to build on top of that. All of our products work, as I said, multi-platform, Linux, Windows, what have you. They plug into the normal IDEs that you would want to develop in, so it's very simple to get engaged with them. We even ship some of our products with Microsoft's environment in there. As I said, if you want to learn more about threading building blocks, you can go, and it's open source. So why multi-core? This probably seems very obvious to this audience. And tonight we're going to actually honor Gordon for his work, pioneering work here. But it's quite straightforward to understand that what Intel builds is performance. That's what we build and sell, is performance through silicon. And it's also not going to come as a surprise to anyone in this room that power and performance are not a linear relationship. And if you continue to build performance, power is growing at a squared rate. So this is all, I should say, normalized to 486 performance, just to give you kind of a relationship between what the power and performance scale that we are looking at. So several years ago, we had a lot of internal dialogue about what we were going to do. How are we going to continue to build performance, which is the core of our business, and deliver that in a way that fit into the power envelope of what we thought was very small at the time and has only shrunk since. So if you think back 5 to 7 years ago, laptops were not the predominant way that people did computing. They used desktops. The power envelope of desktop, of course, was significantly higher, and we were worried about that. Even though we knew that Moore's Law would extend out for another foreseeable future, we were very concerned about the power. So I want to just give you a little bit more on the motivation. So on the, I guess on your left is performance, normalized to 1, and on the right is power. So if we double the performance, or overclock 20%, right, we see the nonlinear power grow. So it's obvious that if we take down performance, right, power goes down. So it wasn't really that complicated to figure out. We had to deliver performance through cores instead of through gigahertz. So we made a fundamental shift in our product line, which is coming out right now that you're seeing between the Core 2 products and then everything after that, quad core, 8-way, 8 cores coming behind that, goes on and on. And we said we're going to be very focused on delivering performance through cores. So we shifted the power wall, which we called the linear problem, the power wall, to a software problem. And at the time, I think the software people thought, hold on, this is a really big programming challenge. How are you going to take advantage of this, Intel? But Intel is predominantly a hardware company, so the significance and the magnitude of the task ahead of us might not have been as well understood as it is today, 5 years later. And our organization, I'd say, easily a third to almost a half of them are focused on this problem, either through tools or through research. So what I'm showing here is the percentage of Intel volume that has shifted from single core to multi-core. So as you can see, we're approaching 75% at the end of last year. So right now, we're basically way towards 100% of our volume being multiple cores. That'd be 2 cores or greater. So as we look forward, this problem, I like to think of it as a challenge. For computer scientists, it's not really a problem, a challenge, is looming large, right? And we've done a lot of work, and Wei is going to talk about some of the work we've done to get ourselves in very good shape, I think, for 4-core machines. But when we start to talk about 8-core and above, I think one of the things we're here to talk to you about is how can we get some help and engage more deeply with academia in working on some of these problems to make parallel programming easier, because not everybody's going to be able to become a specialist in parallel programming. So those are the things that we're thinking about. So our job is to make sure that the software industry makes the most of our performance, and I've talked briefly about this problem, which is the growing gap. And that's the focus of Wei Li's efforts and the rest of the technology discussion. Today, we're going to talk about parallelism within an application. Everybody here knows about all the different kinds of parallelism. We wanted to focus today's discussion a little bit more finely into a specific area. Not to say we're not working on all of these other problems, because inside of my group, we are actually looking at all the different software parallelism issues, each one with its own set of projects and complications. So, not to spend too much time on the tools, because it's all things that you can learn about. We are working and will introduce, as I said briefly in my introduction, in this next year, what you'll see from us is a full suite that's very organized around discovery of parallelism. Expression is where most of our tools are today, and we have the bulk of our work has been in expression and what we're calling confidence, which is the debugging phase, and then tuning. But we're really right now focusing our next set of tools on the discovery and trying to make that easier. I want to mention a couple things about our university program before I sit down, because I won't come back up except to answer questions with Wei Li. We have accelerated our university program in the last couple of years. These are universities that we're engaged with who have curriculum on parallel programming, where we're actively training developers today. We're starting post undergraduate training now, or retraining for people who may want to get more familiar with what's going on. We, as I said, have launched all of these online capabilities. And the last thing is, you can always now come to Intel, to intel.com, and ask for a live person to engage with if you're stuck on a problem. So we've kind of tried to set it up so you can get online experts, and then you can actually get a live expert if you get stuck, and try and help people through this. At Stanford, we are engaged on a multi-core program. We've, of course, donated equipment and funded some research. There's several courses that you can see that are supporting the curriculum, much of which Wei Li is going to talk about. We are very interested in doing more, and so part of our discussion today is hopefully to pique your interest in what we're doing and enroll people further. So with that, I'd like to introduce Wei Li, and you can ask questions at any time. Please feel free to interrupt, and Steve will poke Wei Li, I'm sure. Wei's taught here before, so he knows what to expect, and I'll answer anything else that you might want to know.
Hello, can you hear me? Yeah, it's working. Okay, thanks, Renee. Glad to be back. Actually, I was teaching here 2 years ago with Professor Jeff Bowman teaching CS243 advanced compilers. And was in the other room, so we were actually wandering into the other room, so that was the room for this presentation as well. Anyway, glad to be back. So let me go to the next slide. So challenges for parallel programming. Now I was thinking about this particular topic here. I remember about 20 years ago now, make me feel old. When I was a graduate student like you, I was working on compiling for parallel machines. So I was, my PhD thesis was actually on compiling for Newman machines. I don't know if you have heard about the term Newman here. Yeah, it's coming back also, right? So we're using Kendall Square Research, that probably tool for you. BBM Butterfly, that was what I used for my thesis. So 20 years later, we're still talking about challenges for parallel programming, right? So now, what's the difference, right? So we, 20 years ago really was a golden age of parallel programming. Actually, it was a lot of funding from DARPA, a lot of funding from NSF. A lot of us young graduate students work really hard, try to make it work for high performance computing. And we made good progress, actually, in the past 20, 30 years. So now, what's different? Well, the difference is, used to be at the beginning of the introduction, used to be parallel programming was part of this high performance computing domain, where it was very much a niche market, right? We got a lot of good people try to parallelize various different applications from national labs, from big companies doing simulations and so on, and but was very much a niche market, okay? And it's very expensive to buy these machines, by the way, buy these supercomputers as well. So now when I'm looking at what I have, right, this is Lee's laptop. I don't know what he has, but my laptop, I was running some parallel program yesterday, and I find out it was a 2-core machine, and actually I can get speed up on my laptop. It was really in some sense, it's a parallel machine. It is a really true parallel machine, the tiny laptop I have there. So you don't have to spend multi-million dollars to buy parallel machines anymore. You have these machines everywhere. And as Renee said, this is Intel's direction. We're going pretty much everywhere with multi-core. So that means we really need to look at different applications, right? So no longer the applications people do in national labs and so on. So what kind of new apps do people do, right, on your laptop or maybe on your desktop? So a group of people in our organization, they were thinking about this problem. They say, what can I try when we try to thread other applications? So as compiler team, the obvious thing is, hey, can we try the compiler itself, right? And we try to learn what kind of things we may run into that other people will do parallel programming that most of the national lab people will not run into, right? We're no longer in the domain of Fortran, looking at the matrix computation, matrix multiply, and so on, right? So what are the new apps we may want to parallelize, and what are the new issues people run into? And as a result, as a tool of the organization, what kind of tools we want to develop? Okay, so that was sort of the original motivation to try out one example here. So I'm going to share you the things we have learned, and then after that, we'll share with you what kind of tools we're building within Intel. Okay? Again, feel free to ask questions. I think I need to stop before 5:15. Renee has something very important to go to. But we have time. Just feel free to ask any questions as we go along. Okay. So, how many of you have taken compiler courses? Most of you. Good. Okay. So you know roughly what's in the compiler, right? And usually we have a front end in the compiler, and then we go through a whole bunch of optimizations, and then we do code generation at the end, right? And also nowadays we're looking at sort of more advanced optimizations like interprocedure analysis. You need to look at multiple procedures at the same time, right? So intuitively, when you are compiling a set of files or set of routines, you would think the compiler should have enough parallelism, right? There is parallelism in the compiler, right? Because that's obvious, because when you compile one routine versus the other routine, these things are usually independent. You don't depend on, well, usually they're independent, right? At least the first phase of it. Yes? With me so far?
Optimization, which propagates dependencies potentially through your whole program. So.
Yeah, that's right. That's a good point. So for separate compilation of these different procedures, they can be independent, but so there's a phase in between where you want to collect information from separate procedures, then you merge it, then you go parallel again, right? But at the high level, at the coarse grain level, they are very much parallel, right? Okay? So you would think we just parallelize it and then, get a lot of parallelism, speed up from this, right? So this is the high-level architecture of the compiler, where we have mainly, don't worry about the details, but at the 3 different levels. At the high level, we are going through different, parsing different routines, and then we compile different routines, right? And then for each routine, you will go in there, you do a whole bunch of optimizations, your favorite optimizations. Yeah. And then once you're done with the optimizations, you go code generation, right? So in the middle part is the code generation, is the optimization, and then the last part has the global optimizations and also the code generation in it. Okay, so that's very simple. Now, when somebody who knows the compiler very well, so he would just go in and say, hey, where do I want to parallelize? So they sort of roughly know where it is, right? So here, we want to go as high as you can, right? So the difference between what we do for this kind of application versus, the typical numerical application is numerical application in high-performance computing, you tend to look at sort of single loop nets, right? And you have enough of matrix computation going on, it is sufficient for you to get performance, parallel performance out of this. But in this case, what you really want to do is go as high as you can, right? So the highest you can go is the main procedure, what we call main.c here. And you go in there, you look for one particular loop. The obvious loop is the last loop. That's for each function, you optimize this, right? And that should be a very straightforward way of getting speed up there. So let's try to parallelize it, right? So you can use your favorite, programming model, either creating multiple threads or OpenMP or whatever it is, and try to parallelize that particular loop. Okay? No questions?
Presumably, there's a higher level, which is just the standard parallel make files, the parallel make program, which works pretty well.
Yeah. So yeah, that's right. So in a real setting, this will work very well. And the reason for this is actually the 2 reasons. One is we want to use it as a test case to see what happens. So this doesn't have to be very realistic. But the other, there's also a realistic reason, which is, as you said, we do IPO, right? We do interposition analysis. Ultimately, everything is actually at link time. So you do have to worry about this. And parallel maker will not work anymore in that case. Okay. So you do parallel. Then what we find out was, surprise, surprise, it's not parallelized, right? It's not even generating the right code, because once you put simple parallel construct over there, you run into a lot of dependencies. Okay? Now, why do we have all these dependencies? I guess you all know the definition of dependencies and all that, right? I don't have to introduce that. So that usually means when we design a compiler, I think we just started at least more than 10, 15 years ago. At this version, well, we made a change along the way, but this particular version actually started, at least the middle part started about more than 10 years ago. Right? So when people design something like compiler, they didn't really have this multi-core in mind, right? They didn't think, oh, 10 years down the road, we need to parallelize, right? So when they designed this, they treat it as a sequential program. Okay? And as we imagine this may be true for most people outside, even now, right? Or as ISVs, they never, when they design a code, they usually don't think of parallel. So as a result, we have quite a number of global variables in it, right? You know what global variable is, right? So when you have a global variable, you have all kinds of dependencies. So even conceptually, that particular loop can be parallel. Because of those global variables, you have dependencies. So one guy updates that global variable. The other procedure is, the combination of the other procedure is reading that global variable. You have a dependency. And that's really artificial, right? Because from pure algorithm perspective, it should be parallel. But because of the way we implement it, it has dependencies. Okay? So in this particular case, we have something called threshold. So in the compiler, we have all kinds of heuristics to decide whether we want to do optimization or not, and we have some kind of threshold variable inside. Okay? So when we're looking at this particular way of doing parallelization, what we find is you're really talking about parallelizing something which is much, much bigger than a loop nest. Okay? We're talking about something, the code involved in these parallel regions, actually they're spread it across a few hundred modules, actually probably 200 modules. And also, and actually there are a few thousand lines of code, actually it's close to 500,000 lines of code. So there's a lot of code involved in order to make this thing parallel. Okay? And we also look at how many global variables we have. It turned out to be, they're close to 4,000 global variables. Right? It's not an easy thing. You can just eliminate something and make it work. The compiler itself also has a serial portion. Right? So it's not embarrassingly parallel. It does have a serial portion, which is conceptually when you finish your compilation of each procedure, you need to write out. You have I/O going on. You dump to .obj file or dump somewhere. You do have serialization going on there, and that's something you cannot parallelize. You do have to dump the stuff out sequentially. Okay. So how do we resolve these things? So our team basically, used some of the tools I described a bit later, and then go in, identify these various different global variables, and characterize them in different categories, and then try to figure out how to fix these dependencies. Right. So when you have things like a global, you may have, you may be able to, in some cases, if the global is read-only anyway, and you're fine, right? And if the global is always defined before it's used, and you're fine also because you can actually privatize it. You can, instead of using global variable, you make it local to that particular thread, and everything will be fine, right? So there are different ways we can do to eliminate these dependencies. And in the worst case scenario, like the I/O case, you have to put synchronization. So you actually put locks around these things and then serialize those. Okay? So we actually managed to make it work, but it took quite a bit of effort, and it was a good learning for us actually, even as a compiler person, to see what the user may do when they're working on an application like this. Okay? Yes.
So you took an approach of taking an existing code base and massaging it into a parallel one. Do you have a sense for how close to the ideal you got versus if you had to throw it all away and rewrite it the right way?
That's a good question. I don't know. I think what we managed to get is very decent. I don't have the numbers with me. We get somewhere around, we tried the compiler on a set of benchmarks and measure the compile time. I mean, that's what we're getting, right? So on the 4-socket machine, each has 2 cores. So you're talking about parallelism of 8. We're getting somewhere around 2x. Okay? So you may look at 2x, you can look at differently. You can say 2x is great, I got 2x. And you can also look at us and say 2x out of 8 is nothing, right? So now the interesting question is, what is optimal? How close are we to optimal? As you all learn, M-DOS law, right? So it's not like we can have magic, everything will be parallel, right? So we actually looked at what is the best you can do for these cases. They're somewhere around 3x. That's the best you can do. And so we managed to get 2x out of 3x. I think in terms of that effort, it's quite reasonable. Now, obviously, can you? I'm not sure. Yeah, I probably didn't quite answer your question. So the question is, can you redesign your compiler algorithms so that you can actually get AX? And that's more of an open question.
Or avoid global variables at all, because in your assumption it's sort of fitting that you use, for instance, procedural languages, but you could also rewrite the entire thing in a way that you don't have to deal with global variables, right? That's
yeah. So there are two ways of doing this.
Yeah.
I think ultimately, if you have different algorithms, that will give you the the best you can get. And short of that, if you can eliminate the use of global variables, say we actually implement our compiler using C, right? So if you have a functional language, you have something different. I don't know. I mean, this is more academic discussion, right? So what can you get? And I remember, 15, 20 years ago, somebody actually did a thesis on parallelizing the compiler itself. And you can check that out, actually. A friend of mine who got his PhD from Rutgers with Barbara Ryder, if you know her. So they showed in the compiler itself, inherently, if you only look at one procedure at a time, the amount of parallelism is not that much. But we are doing that across procedures. You may actually have a better luck with that. Yes?
So proportionally, what did you find the bottleneck? Was it the global variables or the inherently sequential part of the compiler?
The bottleneck in this case actually is global variables, because if you look at the example I showed earlier, because we're doing it at a high level, when you compile individual procedures, they are conceptually independent entities, right? So you should get very good. Now, obviously, we have a front end before this, so we cannot parallelize the front end part. So we don't have 100% available to us. So it depends on your input data. So your benchmark may be, if your benchmark has only one routine, there's not much you can parallelize, right? If your benchmark has hundreds of routines, then it's easier for us to parallelize. Yes?
So you're not seeing a change in memory technology, a la what Burton Smith has tried to do?
I'm not seeing memory.
You're not seeing a change in memory technology, a la what Burton Smith is trying to do with full empty bits on memories and stuff like that? Memories.
I missed the connection here. What?
Transactional memory is one of the things you can do. Yeah, well, Burton did the multi-threaded architecture, the Donnell Core HEP, and a number of other machines that he's not at liberty to talk about.
Yeah, yeah. I actually talked to Burton a few weeks ago, or a few months ago, actually.
But so you're not seeing any fundamental change, though, in how people are using memory. Memory is just going to be memory to you.
Memory is going to be memory to me, but if you're talking about synchronization, if you want to go further, transactional memory may help here. We didn't try transactional memory. Actually, I will talk about transactional memory later. We didn't try it, but it may help.
Did you try it on 4 cores and still get a 2x speed up? And also, was that wall clock time?
Yeah.
Time?
Yeah. I don't remember the number because I was not the one who did it actually. So I can figure out.
Inherent speed up. There's about a 20% inherent parallelism. And I'm just wondering if the difference between that 1.2 and the 2x is just due to having the operating system run on a separate core.
Heavy operating system? No. I don't think that would be a reason.
I mean, you could figure that out, by knowing whether it was wall clock or CPU time sped up by 2x.
Yeah, I don't think that would be a reason, but I'll dig out more data for you. Okay, so now, so I'll give you an example. Right? Example is sort of on the positive side, you get something. On the negative side, we actually require quite a bit of work. So what tools can help you? As Renee mentioned a bit earlier, so in terms of parallelization effort, mainly we're looking at sort of 4 different steps, right? You start from application, you need to figure out what kind of parallelism you have there, right? Because sometimes easy, sometimes not, right? And once you know where the parallelism is, then how do you express it? You have different programming models for it. And once you have a parallel code, your job is not done yet. You need to make sure it is correct, and that's not easy to do. And once you have a correct program, you need to make sure your performance is there, because ultimately you're going there for performance, right? So let's look at these things one at a time. And as you may have noticed, some of them we already have products for it. For example, compilers, we already have a product for it. and the library, we have product for it, and some of them we don't have is Intel TBD, right? So these are the things we are working on right now, actually. So the Discover product is actually, one of the things a team I have is working on right now. We don't have a product out yet, but they're still at the early stage, and we're certainly interested in collaboration with academia on this also. And some of these things you may have, as Renee mentioned earlier, these things have, they're actually quite sort of state-of-the-art products the industry has as a product. And they also have roots in research academia also. For example, the confidence, the Threadchecker, and both Threadchecker and Thread Profiler, they have the technologies originated from Cook and Associates. Dave Cook was a professor at the University of Illinois many years ago, and he's with Intel right now. So some of these tools have a long history, and some of these things we're currently working on. Okay, so I'll mention to you a mix of different kinds of things we have here. Okay, so what is Discover tools, right? And as we mentioned earlier, when you parallelize the compiler itself, right? And you need to figure out where you have parallelism. So in that particular case, because we're compiler guys, we know, if you've been with the compiler team for a while, you know exactly where to find these things. But recently I've been going out talking to customers, right? And part of the benefit of being in industry is we got to work with our ISVs and to try to figure out what kind of code they have there. So instead of talking to the national lab guys we used to talk for many, many years, we went to talk to some very small shops. I mean, there are people like 10-person company. There's one extreme case is a 1-person company we talked to. But we had actually look at different applications like insurance company, right? Or games when people look at these things. So in these applications, they may not have somebody who understands everything, right? So what we want is to have a tool to help them figure out where you have parallelism. Okay? So that's what the Discover tools are the design goal for this. So we want to not only take input, it's going to be an interactive tool. We not only take input from user, but also provide recommendations in terms of, this is a place we think it's better to optimize, and this is a place we need some help from user to make it more parallel. And the reason we're doing this interactive tool is for those of us who've been working on parallelizing compilers for many years, it was a dream, right? If you can automatically parallelize everything will be cool. But it didn't quite work out that way. So automatic parallelization is not very, it's not practical. And I think we think that the right thing to do is to have an interactive tool so people can do that. Okay. So here is just a screenshot of what we think this may be. And again, it's not finalized yet. And basically, if you look at a call graph, this is a call graph. If you're a cook, you call 2 different routines. One is called cook meat, the other called cook veggie, right? If you're a cook, I guess you do both. You want a balanced diet here. And then in both cases, you will call a routine boil pot. Okay? So in that case, cook meat and cook veggies, they're actually parallel, right? But you also share something, right? So in that case, what we want is we want to be able to get into the code and then analyze it and then make a recommendation to the user saying, hey, we find out, at the highest level, cooked meat and cooked veggie, they may potentially be parallel, right? But this is something you cannot do automatically within a compiler because they actually share something, right? So we will say they may be parallel, but they have dependencies. They actually, have sharing. They all call a procedure called boil pot. Right? And then the user can look at this recommendation and then figure out, we may want to have a synchronization around boil pot, and then everything will be fine. Okay? So that's at a very high level of what the user interface will be. Now, in terms of how to implement this internally, so we're looking at the various different kinds of technologies to make this thing happen. Obviously, we need a GUI for it. and we need to make sure it is easily, it's usable by a lot of people, right? But the core of this is not the GUI part. The core of this is the analysis part inside, right? And we have been looking at different kinds of analysis. So we are leveraging technologies developed in the past 20, 30 years in terms of static analysis like compiler technology, right? So we're grabbing some pieces from the compilers to do some analysis, figure out at the compile time how much you can do here. And also we're looking at dynamic analysis, looking at binary instrumentation to run things and give us some dynamic feedback to figure out what kind of dependencies you may have here. Okay? Questions so far? No? Okay. Now the second type of tools we have is express parallelism tools. And it has quite a few components in it. So basically looking at compiler plus a whole bunch of libraries. Okay? And one of the libraries Renee mentioned very earlier was threading building blocks. Well, it's really designed for C++. In a compiler, we actually support something called OpenMP. So how many of you have heard of OpenMP? Wow, okay. So this is a HPC community here. Because when we went out to talk to customers, most people, what is OpenMP? Never heard of it. Because we're talking to a different class of customers right now. MKL, you probably know that also. A lot of major computation, IPP, looking at different domains, it's also a library for it. So let me spend a few slides on two new things we have done recently. Okay? One is TBB. Okay? So why TBB? Because we're talking to new customers who are actually not HPC guys. They're working on their client machine, building software for their client machines, and they probably use Windows, right? They're not Linux type either. And on Windows, the current way of doing parallel programming is actually very primitive. I don't know how many of you have used Windows threads. How many of you use Windows threads here? A few, okay. You have to create threads, you have to wait for all threads to synchronize, you have to manage threads. I mean, it's the simplest example we have here, hello thread. Actually, not hello world, hello thread takes quite a bit of coding to do, right? So that's the baseline we're starting with. Now, what does TBB do, right? So TBB is designed for C++. You can think of it conceptually as a new language, even though the implementation-wise, it's not a new language, it's just a library. All you need to do is go to, I have the link right here, www.threadingbuildingblocks.org. It's open source right now. You can get source as well as binary. You can just go there, download a library, and then link with whatever compiler you're using. Could be Intel compiler, could be Microsoft compiler, right? So it's a library, not a language, but to the user, it's more like a language extension, actually. So if you look at the right-hand side, we have a few templates, parallel algorithm templates. For example, there's something called parallel for, right? So that means you have a loop. It's like a for loop you want to do a parallel version of it, okay? So let's just take that as an example. Say we have a sequential example which does, I don't know what it does. It's just some kind of matrix operation, right? It's very, very straightforward. And then how do you parallelize it? Now, if you need to use Windows thread, you have to create a whole bunch of subfolders. Now, if you use TBB, what you can do is actually very simple. And so we actually basically have two different functions here. The top one is defining the thread body, the amount of work you need to do in the thread body, right? And so this is update velocity body. And then in order to parallelize it, you just call something called parallel for, and then you pass a few parameters to it, and then that's all you need to do for parallelization. Okay? So it's very straightforward, and I understand the C++ guys really like it because it actually has the strong C++ flavor to it, which is different from OpenMP. I mean, some of you are more familiar with OpenMP. The trade-offs between these two, but for C++, OpenMP has its limitation, and this is much easier to do. Yes.
Have to guarantee independence of loop iterations, or
yeah. This is not an automatic compiler. It's not an automatic parallelization library. You have to make sure you're independent. Yes.
So is the entire point going to be you parallelize it for n, where n is a fixed number that you specify compile time, or is it going to be like, I want you to parallelize given the system that has, 512 cores, for instance, as well?
Yeah. So the beauty of this thing is actually, if you do Windows thread, you have to manually manage the threads, right? But here, the library itself does not only managing the number of cores, but also managing scheduling for you as well. So you can do different ways of doing scheduling.
So how does this compare to the Java concurrency utilities?
Java concurrency utility tends to be, Java is more designed for multitasking kind of thing, not really for performance. And this is more designed for performance.
This is almost a direct cut and paste of what you can do with Java as well. They have the same set of tools for this particular example.
Yeah, but performance-wise, I think there's a very big difference between this and the Java implementation. I mean, Java you can do parallel, there's no problem, you can do parallelization, right? But Java threads are very heavy threads. Yes?
Just an implementation question. Do you use a resident thread pool for this, or do you create and destroy threads on demand?
I'm not the implementer for it, but I believe we use resident threads for it. We don't, it's too expensive to dynamically create these things. So I wouldn't be surprised. Just you manage a set of threads and then you schedule that way. Yes?
So how do you, as a programmer, how do you know when it will be worth paying whatever overhead it is to set up this parallel loop versus the speed up or performance? As a programmer, you have to have a gut feel for how much, whether you can get parallel performance out of it, right? So that's the initial stage, right? Actually, that's a good question. So there's a big difference between HPC programmers and the mainstream programmers. Okay? So when I used to work with HPC programmers, they never asked that question, right? They just, because they know they're going to get something out of it, right? So they spend their time, they tune for it, and they will get it. And when I talk to my mainstream customers right now, I often get asked, why should I spend my time doing this thing, right? I need to know whether it's worth my ROI for this, right? So as a part of the Discover tools we're doing right now, we're actually doing a performance estimator. So we're doing estimator to provide, some kind of 15-minute quick feedback and to tell them, hey, do you want to do this or you don't have to do this? Yes?
So by your examples in C++ and C, are you basically drawing a line where Intel is going to support only that language as opposed to any others? Because,
no,
traditional...
I didn't say that.
Okay.
I didn't say that, but our current strength is C, C++, and Fortran.
So you are going to support Fortran, the traditional HPC.
Oh, yeah. We're not dumping them. We still want to keep them as happy customers, but we certainly want to shift to mainstream programmers.
I think I have a question. What's your experience when you deal with processes, for instance? So they are more elevated and it becomes to the real challenge. What's your experience with really parallelizing processes and then can you apply this schema still? Or?
This is for threads, actually. It's not for processes.
Yeah.
Now, if you want to do processes, then it becomes, the trade-off would be different, right? You have to find enough work to justify the overhead. Okay, let me run faster because I'm running out of time. So the other new things we have done recently is transactional memory. Now, you asked a question a bit earlier. And this is not even a product. Okay? The one I mentioned earlier was a product. And this is a prototype which is put out on the website. Actually, Intel has a website called whatif.intel.com. It's a place where we're putting some interesting stuff for people to try. Google has Google Labs and IBM has something similar also. So we actually started something like this recently. So transactional memory, it's called software transactional memory. And I guess, do you guys know about transactional memory or you all know about transactional memory? Okay, so I don't have to explain what it is. And basically, we have a compiler and a runtime out on the website. And this is sort of example, that shows how you get actually use the syntax we have. And I know Christos, he's not here today, in the CS department actually he has a group working on TM as well. And we have a different syntax in terms of describing transactional memory. He's mainly OpenMP syntax. And we actually have an orthogonal approach, meaning we have a TM syntax which is orthogonal to different ways of parallelizing it. Could be OpenMP, could be, could be a Windows thread, could be anything, right? But the idea is very similar in terms of supporting TM. Okay. So the third set of tools is what we call correctness tool. As I mentioned earlier, this is more of an older set of tools we have, which make sure you have a correct program. And as you know, for those of you who actually have done parallel programming, it's not easy to figure out bugs, right? It may not even be deterministic. So we have a tool to help you figure out whether your data races or not. Okay? It's an instrumentation-based technology. So when you actually run it, it takes some time to run it, but that's the best we have at this point. Okay? The best industry has actually for this kind of tool. Yes.
How thorough is the Threadchecker? Does it do the static analysis? So can it discover all possible states?
No, it uses static analysis to trim down the amount of instrumentation you want to do, but it doesn't do static analysis of possibilities. It's a runtime based thing. Okay. This is just a screenshot. Running out of time, I won't go into detail here. The last set of tools is performance. So once you have a correct program, you need to figure out whether you have performance or not. So there are many different issues you need to figure out whether you have load balancing, for example, right? So we have a tool to tell you how well you're doing in terms of performance. Okay? And as somebody asked earlier, how do you know you get performance? So one way of figuring it out is you do the work and then you validate to see if you get performance or not. And then you do more tuning using that tool. Okay. All right, so this is just a screenshot of the thread profile. Right? All right, so with all these tools, what do user get, right? So I have two examples of what kind of performance user can get. So this is just a simple example from is a real application from Russia, actually, because we are so global now. We work with customers everywhere. It's a weather forecast application. And so when they are more migrating away from a Cray machine that they had for a while to Intel machine. And at the beginning, we tried the out compiler. When they compare against a Cray machine, the Cray is actually a CPU machine. So we have a single core performance against a core machine, a processor machine. We're beating them by 20%. Okay? But that's probably a very old Cray machine. Then you apply more advanced compiler optimizations to it, and you got 2.5x. So you actually increase by 2x about baseline. And then you do some source code change, add some derivatives, you get more performance over there. And then you add OpenMP to this, you got like 10x performance on a 4 CPU machine here. Okay? So tools, do make a very big difference if you use it right. Okay?
Is that 4 dual core Atheniums?
These are 4 single core Athenium. Actually, data is a little bit old actually. Not the amount of zeros we have.
So I'm interested in what happens on an 8-core machine, because clearly this code was designed to scale well to 8 CPUs on a Cray. Yeah. So the question is, how well does it do on the Intel?
Yeah, I don't know. I don't have latest data for it, but on 4 core seems to be reasonable. I mean, 2.5 out of 4.
So does the tool avoid excessive parallelism because of the memory bandwidth flow that can be cache image?
Yeah. So we have usually the tools. Usually, for example, compiler doesn't pay attention to bandwidth, but we do have optimization, mainly actually doing prefetch, because we find data prefetch is a two-edged sword, right? On a single core, usually, if you're very aggressive on data prefetch, you get a lot of good performance out of it. But then when you run it on multi-threaded machine, all of a sudden, hey, it's just too many useless prefetch going on. So that's part we actually have some way of tuning for it to control the amount of bandwidth at runtime. Well, at the runtime, yeah. So you have checks on. Okay, so I'll skip this example because I'm running out of time here. Future tools. In addition to what I told you earlier, we're also looking at a few other tools. For example, program model obviously is a big question here, right? So when we want to raise the level of programming abstraction, what is the best programming model for that? The current way of doing threading may be still too low level. Right? Heterogeneous computing, when we go to multi-core, things may be different. What's the programming model for that? Somebody asked, are we only looking at C, C++? So far we are, but we're also looking into whether we should support Java or .NET, right? But so far, for example, Java on the parallel side tend to be is the server side, and you have more transactional process, and it's not a lot of opportunity for doing parallelization. And .NET tend to be on the client side, but they do a lot of GUI kind of stuff, so there's not a lot of computation there either. But we will see when these languages pick up. We will support those as well. And the other thing, people have me ask is Web 2.0 kind of thing, right? People are doing all kinds of scripting language nowadays, and what kind of tools we can provide for that. That's another thing we're looking into. And we have a binary translation tool, which is very effective. Actually translates from x86 to Artanian. And we'll continue to look into binary translation technologies, as well as dynamic applications. Okay. So the last slide is call to action, right? So I've told you what we have. We've made a big progress. We have a good set of tools, but obviously we're not there in terms of solving the parallel programming problem. And it's up to you guys here who are doing active research. You may have a lot of PhD theses you can do on this topic. And once you get great ideas, come to Intel, join us, do something interesting. So with that, I think that's the end of my part. Other questions? And maybe Renee and I can both answer your questions.
But I think we're almost out of time.
Okay. Okay.
I mean,
one more.
Yeah. So if the current model of threading is too low level, what's the replacement?
That's a good question. We don't know yet. I mean, people have been thinking about various different ideas. If you follow, for example, your CS department. Are you from CS? From the Oh, you could. Yeah, I actually read you before. Okay. In CS department here, they're looking at different domain-specific language, right? And if you look at the stuff, Dave Patterson did at Berkeley, looking at all the doors, splitting doors, and so on. So there's some interesting ideas coming out of it. But I don't think the question is answered yet. We're still. Yes.
So how well does STM work in your experience? Can you comment on
which
STM? This
STM?
Right. Yeah.
I think that's still early, right? I mean, transactional memory certainly has its appeal in terms of the problem it's solving, but it also has. I guess you all know the potential benefits in terms of speculation, composability, all that stuff, right? But also has, sort of what I call things that have not been resolved yet, right? I mean, there's memory model issue. I don't know whether you guys look into or not. You get a very, very non-intuitive behavior out of it when you're not careful with memory model, and so I don't know what would be accepted by user when they debug their thing. They look at I expect the value to be 5. All of a sudden you give me 2, which I cannot find the interleaving to get 2. Right? That is non-intuitive way of getting there. And the other question is whether atomic construct is the right level of abstraction. I mean, that's, to me, maybe we need to do somewhere above that. I think we're running out of time. Thank you.
For information on other online Stanford seminars and courses, please visit study.stanford.edu.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.